Welcome to Chapter 6. We're going to take a look at some of our homework problems, the use of StatCrunch, and a little bit of the theory to help you. First of all, in the beginning of Chapter 6, it's important for you to visit your multimedia library. Take a look at your PowerPoints and animations and resources before starting your homework. We do not cover Section 6.7. However, 6.2 to 6.6 are important and you should take the time to look at the material. In the beginning of the homework, we start off by looking at an example of the continuous distribution called the uniform distribution. This first problem is a uniformly distributed data set. A statistics professor plans classes carefully so that the length of classes are between 45 and 55 minutes long. Find the probability that a given class period runs between 50.5 and 51.5 minutes. The first thing you do is sketch a rectangle. A uniform distribution is written as a rectangle. In this particular case, the length of your rectangle goes from 45 to 55. That's 10 minutes difference. The area of a rectangle, as you know, is equal to length times width. So if our length is 10, and we know the area is 1.00 or 100%, that means the height must be 1/10 or 0.1. We then go to the second part of the problem. The class runs between 50.5 and 51.5 minutes. The difference between that is 1. We take that 1 and we multiply by the height, 0.10, to find the area of that small piece of the rectangle. We get 10%. That means there's a 10% chance that is between 50.5 and 51.5 minutes. Be sure to sketch your diagram for this. You do not need to use StatCrunch for this problem. Number 2 is having us begin to take a look at the normal distribution. The standard normal distribution is what is automatically loaded into StatCrunch. In a standard normal distribution, your mean is 0 and your standard deviation is 1. Most data sets, this is not the case, and you will need to change the mean and the standard deviation in your normal calculator. However, initially, these are the values we use. Look back in your notes from Chapter 3, where we learned first about the empirical rule and z-scores. If a z-score was negative, your value was below the mean. If your z-score was positive, the value was above the mean. If your z-score is 0, the value is exactly equal with the mean. In this particular question, it wants us to find the probability that a randomly selected thermometer reads greater than negative 2.11 and sketch the diagram. So this would be the value, negative 2.11 in part A. They then want to know the probability. Well, how are we going to determine that? We're going to click on StatCrunch. We're going to go to Stat, Calculator, Normal, and we're going to put in greater than negative 2.11. We then get the area in the bottom right-hand box. Notice that currently the default settings are for the standard normal distribution. Mean is 0, standard deviation is 1. All we need to do is enter the z-score, and we have the area. So we're going to copy that z-score. We're going to go back to our homework question, and we're going to paste that in, and of course round to the correct number of decimal places, in this particular case 6, and check our work. On the next particular question, we are given a data set that is not based on a standard normal distribution. In this particular case, we have a normally distributed population with a mean of 100 and a standard deviation of 15. We want to find the percentage of people who score between 90 and 115, or to find the area between 90 and 115. So we are again going to go to StatCrunch, change those values, and look for our information. So in this particular case, we're going to click between. We're going to put our standard normal distribution. We're going to go back, take a look at that question again, verify 100, standard deviation is 15. Excellent. So we're going to put 100, 15, and we want to know what's the chance that they're between 90 and 115, and we're going to click compute. Notice my shaded diagram shows the area between 90 and 115, which is what we're looking for. So we can go back to our homework and round to 4 decimal places and check our work. Number 4, asks us to find the score that cuts off the bottom 10% and the top 90%, separates the bottom 10% and the top 90% of the area. Standard deviation is 15, the mean is 100. So we can go back to the values we had before. We're going to go back to the standard screen. Mean is 100, standard deviation is 15. But we want to know where's the area, the score that cuts off the top 90%. Any IQ greater than 80.776727 marks off the top 90%. So we can come back in here and paste it, and it says to round to 1 decimal place, so we would round to 80.8. Assume that adults have IQ scores normally distributed with a mean of 105 and a standard deviation of 20. Find the probability that a randomly selected adult has an IQ less than 129. So we're going to return to our normal calculator, but this time, of course, our mean and standard deviation have changed. 105 20 and less than 129. So our answer would be the value that's highlighted here blue, 0.8849. Notice that the area below 129 is shaded, which means we have the correct area in our diagram. Again, rounding to 4 decimal places, 0.8849. Practically speaking, this means there's an 88.49% chance that if we had a population of adults, from that population where the mean is 105 and the standard deviation is 20, there's an 88.49% chance that if we randomly selected somebody and tested their IQ, that they would score below 129. Similar type of problems for the next few here. This particular one asks us to find P3. All this is finding the bottom 3% and the top 97%. P3 is, again, notation from Chapter 3 where we learned about percentiles. Mean is 100, standard deviation is 20. We want to find the bottom 3%. So we want to come back in here, be careful to check those values. And we want to find the bottom 3%. So we're going to put 0.03. And we'll notice the bottom 3% is shaded. So any IQ score below the 62.38. So again, we're going to round off to the nearest hundredth in this particular case, and we have the correct answer. Now, this next one is one that students often get frustrated with. But what we're doing here is we're given a very small number of data sets to work with. So we have 3 randomly selected households, and we want to look at the possible pairs. If we only pick 2 at a time, what are the possible pairs we could have? Well, again, you could have, and they said they're randomly selected with replacement. We learned about that in Chapter 4. That means we could have a pair of 1 and 1, or 1 and 2, or 1 and 12, or 2 and 1, and 2 and 2. So they already wrote out our pairs for us, and they want us to find the variance of each of those samples. So we're going to click to copy this and open this in StatCrunch. You don't want to do this by hand. Okay, so we're just going to go ahead, and we notice it's already been copied over. We're going to click Summary Stats, but instead of doing it by columns like we did in Chapter 3, we're going to click by rows. And we're going to, highlight X1 and X2, and all we really need is a variance. I'm just going to click that one. And you'll notice that I now have my row statistics. So the first thing I'm going to do is come here and say, okay, well, how many of those had a variance of 0? 1, 2, 3. So 3 out of my 9 pairs had that. The next option would be, let's see, 0.5, and I have 2 of them. So I'm going to say that's 2 out of 9. Be sure to reduce these if it's possible. The next one we have here is 50. So again, maybe 2 out of 9. And the last one we would have here is 60.5. And that's 2 out of 9. So we enter that. And then we're asked to continue, and it says, to compare the population variance to the mean of these. So if you average these sample variances, how would the population variance compare? And this basically asks you to go kind of think back a little bit to Chapter 5. I'm going to let you mull over that part. Think back to Chapter 5 where we looked at probability distributions and finding the mean and standard deviation. I want you to think about that for a little bit, and then you can answer that question. we're going to move on here. Now, in the next couple of problems, we're going to start to apply the central limit theorem. This is why I asked you before you started the homework to read over your PowerPoints and do a little reading in your textbook. The central limit theorem is based on the idea of sampling. And we're going to jump to StatCrunch for a few minutes, do a little bit here with sampling. So we're going to click on Applets, and we're going to go to sampling distributions. So we're going to start off with this idea of a uniform distribution, which again we know is a rectangle. And we're going to sample, we're going to do sample sizes of, let's say, 30, and we're going to sample 1,000 times. So you'll notice that even though we started out with a uniform distribution, if we take a bunch of samples that are size 30, we end up getting something where our sample means, in other words, plotting the averages of each of those samples, ends up kind of looking normal. And of course, if we did more of these, you just get a little bit more of a precise normal distribution down here. Certainly, if you pick a larger size sample, you get less variability. But that worked, notice, even with a uniform distribution. Now, if we went to a small sample size, you're going to get a little more variability. So you want to kind of explore and try to figure out what's the magic number that really starts to give us that normal curve. And you'll find that it's a sample of size 30, greater than 30, guarantees that we're going to have a normal distribution, even if we started off with something that wasn't normal. So let's go back and take a look at a right skewed. Now remember, right skewed means it has a long tail on the right-hand side of the distribution, and we're going to sample these. Again, we're going to use 30 here. We're going to sample 1,000 times. So even though our original distribution is really skewed, our resulting distribution of sample means is normal. Again, every time we took a sample here, we would average the results and we'd plot the average. So this is a distribution of our sample means. Again, we could do it 2,000 times, 3,000 times. We still notice that we have a normal distribution. We're going to go back now and do a bell shape, or of course a normal distribution. So you're going to see that this one pretty obviously comes out to be relatively normal, even if we only did samples of size 2. Certainly if we do 30, we get very little variability there. Notice you don't have to go as high as 30 if you're already dealing with a normal distribution. So we can even do 10 and still get a normal curve with our results of our sample means. We're going to go back and visit binary. Now, binary is pretty familiar to us. We just looked at that in chapter 5. In a binary distribution, you're looking at two possible outcomes. So you're thinking, how could this possibly start to look normal when we're sampling? Well, let's take a look again at a sample size 30, 1,000 times. And you'll notice we really do get something that looks like a normal distribution. So you want to kind of keep those concepts in the back of your mind as we begin to explore the idea of the central limit theorem. And by the central limit theorem, what we mean is if we're dealing with a distribution, and I'm just going to use the normal one here for right now, let's talk, for example, about women's heights. So, a lot of women are kind of average height. You have some that are shorter, some that are taller, and of course, yours truly, who's practically off the charts. But we could look at a distribution and say, well, we know that most of them are going to be average height. The chance of finding somebody up here or down here is not as likely. Now, keep in mind, though, that there's a difference between an individual and a group. If I sampled a group of women, their average height is going to be somewhere close to the middle. One woman might be really tall, one woman might be really short, but the average is going to fall in the middle. And that's the idea of the central limit theorem, that if you're doing a group, your results are going to start to look pretty much like the population. So let's go back to this problem and take a look at a problem here. Oops. On number 9, it says this one is actually about women's heights, and it says that the mean is 64.7 and the standard deviation is 2.1. And we want to find the chance that if you pick one woman, what was the chance that she'd be less than 65 inches tall? Now, immediately, if the average is 64.7 and you're checking to see the chance that she's less than 5'5", you know that you have at least 50% of all women, because 50% fall below the average. So it's going to be a little more than 50%. So 64.7 and the standard deviation is 2.1. So we're going to go back to StatCrunch. We're going to open up our normal calculator again. And we're going to put in 64.7, 2.1, and we're going to say, what's the chance that a woman is less than 5'5"? So you can see it's just a little over 55.6%. So we're going to toggle back to our homework and round our answer then to 4 decimal places. and we get the right answer. Now, part B asks us a different question. Part B says, what if I selected 50 women? What would happen to their average height? Well, obviously now the average height should definitely be less than 65 inches, but how is that going to change what I do in StatCrunch? So I come back here and I take a look and I say, well, I have standard deviation here of 2.1, but that's for the individual. If we're sampling a group, we're going to be reducing the variability because we're sampling a group. It's going to be, the results are less variable if we're dealing with a group instead of an individual for our sample. So in this, we're going to use what's called the standard error, and you should have seen these in the notes if you referred to the notes prior to beginning this video. You would take the standard deviation 2.1 and you would divide it by the square root of the sample size, which in this case is 50. So instead of 2.1, we're going to put in the standard error, which is 0.2969848,481. Now, typically, you can round off to 4 decimal places. I'm just kind of showing you all of them here for sake of example. I'm going to click compute. So this time we're saying there's an 84% chance that a group of women would have an average height below 5'5", which makes sense. You know, one woman, there's more variability allowed, but for the group of women, we're going to be closer to that expected average. So again, we're going to go in here, pop it in, round it off to 4 decimal places, and check our work. Now, on number 11, we're looking at something called a quantile plot. In Chapter 6, one of the tools we can use to determine if a data set is normally distributed, if you're not told otherwise, is to create what is called a quantile plot. A quantile plot actually shows the plotting of the data points with respect to their corresponding z-scores. If your points lie relatively close to the straight line in a straight line pattern, then you can say your data is normally distributed. However, if they do not lie relatively on the straight line, or they follow some other sort of pattern, then you would say your data sets are not normally distributed. Okay. Of course, if it asks us to create the quantile plot first, we're going to copy the table, open it in StatCrunch, click on Graph, and we're going to do what's called a QQ plot. That's a quantile plot. So we're going to go ahead and have it plot that for us, and then we can take a look. Now, if there appears to be a pattern here, like if this was actually oscillating up and down or something like that, we would say no, there's no normal distribution. If, on the other hand, these points are relatively close to the straight line, very little variability from that, then you would say yes, this is a normal distribution. And I'll let you determine that by exploring a little bit and then answering your homework question. And again, a little video for you to watch closer to the end. Okay. Let's just hold a minute here. We're going to go back and take a look at 1 or 2 more from our study plan. Now, so we want to practice this whole concept of the sampling distributions and estimators and the Central Limit Theorem. So we can come in here, take a look at some application problems. And you know what? Let's take a look at our test. I presume we finished all of our practice questions. And we're going to take a look at our test. There we go. Now it's loading. So again, very similar to a homework question we just solved about determining whether it's a normal distribution or not. Here's one about the capacity of an elevator. So you're going to check what's the chance that a person individual has a weight greater than 151, and then what's the chance that a group of 10 have an average greater than 151. And again, that's where you're going to have to take your calculators out, and you're going to have to divide by the square root of the sample size. Here's one where we're simply going back and determining the cut score using our normal calculator. Here's another one with the women's heights. Very, very similar to the homework question. Here's one about hat circumferences. Uniform class length. Here's one again where we're looking at an individual versus a group. And let's take a look. We'll come back and take a look at that in a minute. There's another one we're looking at IQ scores using the normal distribution, doing some sampling. looking at a quantile plot, reading our z-scores, and the heights of doorways. So we're going to go back and take a look at just one of them here, just for one additional example. And this particular problem is looking at an engineer doing some design for an airplane, and the weights are between 130 and 181. That's what it's designed for. So the new population of pilots has a weight of 139 and a standard deviation of 34.4. So we're going to go take that information, go to our normal calculator, and take a look at how that pans out in StatCrunch. So again, so the average is 139, standard deviation is 34.4. So we're going to come back to our normal calculator, and then we're going to click between, because they want to know what's the chance of certain values between, and we want to know what's the probability that's between 130 and 181. So we're going to put between 130 and 181. So we want to make sure that, of course, the area shaded kind of makes sense with what the question is asking, and it does. And we're going to go back in here and paste that, and then round off 4 decimal places, it says, and we're going to check our answer there. And then it asks us to do the same thing, except for the fact that instead of sampling 1, we're sampling 36. So what's going to change on this page? Well, the value that's going to change there is the 34.4. Instead of 34.4, we're going to have 34.4 divided by the square root of 36, which is 6. So I'm going to put in 5.733 and click compute instead. Okay, so this is showing me that if I sample a group of pilots, that there's a 94% chance that their average height would fall in that, or average weight, would fall in that particular range. Again, I can come in here and, of course, pay attention to the round-off rules, and then redesigning the ejection seat, which probability is more relevant, that for an individual or that for an average. So I want you to stop and think about that, which would be the most pertinent to what we're looking for. Let's look at just a little bit with this last one here, just to clarify, because students sometimes have questions with this one. Men's heights are normally distributed with a mean of 70 and a standard deviation of 2.8. So we're going to come back here, 70, 2.8. And what is the question asking us initially? It says the standard doorway height is 80 inches. What percentage of men are too tall to fit through the doorway without bending? So we want to know what's the probability that somebody would be greater than 80 inches tall. So pretty slight chance, but still there might be a few. So the percentage of men, let's see, we're going to have to convert that to a percentage. Okay, so remember, we're going to convert this to 0.0, so move it over 2 decimal places, 0.02%. Okay, what about women? Well, women, the average is 63.2 and the standard deviation is 2.5. Zero. What this means is not an error. This means exponential notation. So we're saying 9.08 times 10 to the negative 12, and you move your decimal 12 places to the left. Which means basically 0%. Now, if you wanted to design it so that the doorways would have heights that are sufficient for everybody except the tallest 5%, what would you use? So now we have to go back to the 70 and the 2.8. But now we want to make sure that it works for everybody except the tallest 5%. So I'm saying greater than, and I want the tallest 5%. That means the top little tail should be shaded red. Well, that would work for everybody except for the men over 74.6 inches tall. So if you wanted to design a door that would work for 95% of men, you would design your door to be 74.6 inches tall. Only 5% of men would not be able to fit in that door.